Righty then. So I've been talking about models and just kind of bandying the term about without a whole lot of attention to what a model might actually be. So in this one, we're going to spend a little time. I am going to spend a little time talking about what a model actually is. You probably don't care about this at all. The light, that is. I hope you care about models. Okay, so a model in the sense that we're talking about it, it's an analogy to between two things. Now, clearly, a model can be a representation of a thing. You could build a ship in a bottle. That ship is a model. The symbolism of being in a bottle, I'm not quite sure what that's all about, but maybe it's just the skill of doing it. Let's see. Gosh, I was just wandering around thinking about what models we carry around in our heads, but in the context of the previous video, I believe, recent video anyway, prior to Copernicus, the model of the solar system and the universe at that time, for all intents and purposes, was that the Earth was stationary and sat still, and everything else revolved around it. With the Copernicus's work, that the model of how the universe works changed. It went from the Earth being the center to the Sun being the center, at least of the solar system. As I don't know that I read that sentence, but there's a lot to be worked out after Copernicus flipped things around. But still, the model changed, and in the context of another pretty important book, although it's probably fading a bit, is The Structure of Scientific Revolutions. Another book that you should at least know of. It was written by a guy called Thomas Kuhn. As far as I can tell, no relation to Alfred. 1962 was its first edition. It's very complicated. There's kind of two bits to it, but we'll just focus on the first bit. This is the book. This is where the idea of a paradigm comes from, and a paradigm shift in particular. And the quintessential example of a paradigm shift is the Copernican revolution. The development of oxygen is another. The idea of oxygen is another one that Kuhn uses. So that's a model. We have a model of how a college education will go. Sometime in your, for all of you all, sometime in your junior and senior years in high school, you started imagining what college would be like, and you started thinking about how you would find a college, and you carried that out, and some of the things were the same and some of the things were different. You arrived at college and you lived in a dorm, and then you got an apartment, and everything's going along pretty much like you expected, and then COVID-19 happens, and now I'm talking to you on a video camera. So the model of how systems thinking course changed, how we might think of. So what we're doing now is nothing like what we thought we would be doing 12 months ago. Okay, so a model is an analogy. There's 4 minutes of blathering on, 5 minutes of blathering along about what an analogy is. But let's get more specific. Let's all of you. I think it is safe to assume that all of you have ridden in automobiles. I think it is safe to assume that almost all of you have filled a gas tank with gasoline. I'm assuming that all of you know, whether or not you've actually ridden in one, you know that automobiles mostly use gasoline. We'll get to the bit where you're all going, but what about Teslas and all that? Yeah, we'll get to that. Right. So cars, and in terms of the environment, the big impact of cars, or the impact of a car, can be quantified by its gas mileage. Bigger equal better. And vice versa. Smaller equals worse. And why I'm doing this will become clear in another few lectures. And the key, the number that we use in the States is miles per gallon, or mpg, or miles divided by gallons. All right. And there are two clearly important things. There's distance is part of our model. How far did we go? Distance. That's the miles part. And then there's how much fuel we use. Fuel consumed. Oh, never mind. All right. So, and in this model of gas mileage, there is it's a linear model. That is, in this model, if we say that distance, and we're going to say in miles here, and fuel in gallons is a straight line. If we don't, and we'll just for completeness, this is 0 and this is 0. Don't have to do that, but just I'm trying to be good to get off the mark here. So if we go 0 miles, we don't use any fuel. As we go more miles, we use more fuel. And the slope of this line is, well, sorry, is gallons per mile. It's the inverse of that, but still makes more sense to do it this way. We could, we could do it this way, where we have fuel, and we have distance, and we have the model here, and it just doesn't make as much. How much I burned 10 gallons of fuel, so I went some distance d. But it doesn't. We don't think in terms. We don't think of the independent variable as being fuel. We think of it as being distance anyway. So now it's the other way around. In Europe, they do. They measure mileage in liters per kilometer, which makes this make more sense. Yeah, aren't you glad that you took this class? Yeah. So there's that. All right, but now we just got a car, or we just started thinking about our car in a different way, and we're gonna do an experiment. We're gonna say, okay, the manufacturer tells me that my car gets this, and usually, of course, they tell you two things. They give you a number for the highway, and they give you a number for in the city, which is kind of quaint. So we have distance, and we have fuel. And we go for a drive one day, and we drive 20 miles, and we use, we drive 20 miles, and we use this much gas. And we go for a drive another day, and we drive 20 miles also, and we use this much gas. And we keep measuring over and over again how much gas we use when we go a certain distance. And when we get out here going far, they probably kind of cluster a little bit more, and I'll talk about that in a minute. But the point here, of course, is that this is not a nice straight line. We can, of course, draw a line through this, and that is our model. We could actually, doing a little bit of actually not too terribly complicated mathematics, we could calculate what the gallons per mile of calculate the slope of this from the data, get a thing of gallons per mile, and is it the equal manufacturer? Question mark? Question mark? Well, we'll just call claim because it has fewer letters in it. And of course, okay, so data, model. Data is going to be scattered around the model. And we could do another thing we could do is that we could, we could subtract this line from that data, in which case we need a zero line here, and this is a residual, and I'll talk about that in a minute. And this is distance, and it's going to be, those are subtract, what am I doing? I'm doing R is equal to data minus model. So if I subtract, these are all up here, and then some of these, then we get some down here, and then we get here, and then they get more clustered around here. Right, yeah, it's all clear as mud. The point is that there is going to be a difference between your model and your data. And to the extent that these data points are close to 0, we are going to be more or less happy with our model. I go into a lot more detail, well, not a lot more, some more detail about this in the paper called Gilbert MDR, Models, Data, and Residuals. Now, there's one other thing. So I started out saying, well, this is a model where we think about how cars or transportation impacts the environment. Well, this day and age, as California burns to a crisp and dehydrates, we're really curious, we really care about how much carbon dioxide is in the atmosphere. So it turns out that gas mileage can get you, so the impact in terms of the environment with respect to driving your car is putting CO2 into the environment. It turns out that 1 gallon of gasoline releases about 20 pounds of CO2. So if you have a car that gets 20 miles to the gallon, for every mile you drive, you put 1 pound of carbon dioxide into the atmosphere. To the extent your car gets more miles to the gallon, it's better because you put less CO2. So here, let me write that down. At 20 miles per gallon, 1 mile equals 1 pound CO2. So if you get more miles to the gallon than 20, then you're putting less than a pound And if you do the other way around with smaller. Oh yeah, I was going to riff about better or worse here. Out here, you can start to see the effect of weather on your gas mileage. I've driven back and forth between Madison and Minneapolis many more times than I can count. My mileage may vary, and being the nerd that I am, what I've determined is that my mileage, the biggest factor actually is wind direction. If it's windy and behind me, I do much better. If it's windy and in front of me, I do much worse. The other factor, at least in my old car, I had a Volkswagen Passat. The second major factor was temperature and humidity. It performed the best in the mid 50s temperatures Fahrenheit. The current car I have, I haven't driven up and down enough to be able to tell. But it seems to have a sweet spot in weather too, but I haven't figured out where it is. Rightio. Models, I talked about Kuhn, I talked about residuals. All right. There you have it. The next one I will actually talk about a system. Right on. Talk to you later.